Okay, good. So welcome everybody. Thanks, Alex, for the introduction and for having me here and giving me the opportunity to show some of our new work. I apologize for the very generic title. This always happens if, so yeah, Alex asked me a few months ago, and then I said, well, we have so many things I could talk about, and then I really want to tell you some news stories. So basically, that's why we have this generic title, and I will basically show you in a minute what I will talk about. Actually, I'm surprised that I'm the first who shows this picture here. I had it in the slide and thought I had to talk about it. I basically think I don't have. So this is, sorry. Can you see still? Can you see? Do you still see my slides?
Yeah, we see the advanced modeling chemical space slide.
Ah, okay, perfect. Okay, so that was something strange here. Okay, so I think I don't have to talk much about it. It started about, I think, 5 years ago or so, when this topic of this chemical space modeling really get off the ground, and especially Enamine made a big contribution by preparing the real space and make this all available. So at that time, we basically had not a few tools available to actually work with chemical space. And one approach actually to address chemical space is basically to search with some heuristic approaches. So this is actually was done already years ago, and this is actually a slide from a current development here in Hamburg, where we use a classical heuristic search engine to go through the spaces and construct molecules. I think it's obvious that we need some kind of algorithms to deal with these spaces because the spaces are too large to actually enumerate them. So here is a picture of an outline of a genetic algorithm to actually work with these spaces. And the good thing about genetic algorithms is actually that you can create a population based by a combination of fragments following the rules of the chemical space. And then you can use a very generic scoring function to really find interesting molecules here. Yeah, and we can basically use our complete infrastructure with software here and plug this into the scoring function to get molecules. Yeah, so we could use fingerprints, structural alignments, so molecular overlays. We have a pharmacophore matching functionality, so you can search for molecules fulfilling certain pharmacophores, or you can use docking technology actually to create molecules from the space which might fit to a protein structure. So this idea is quite nice, but it's also very obvious that this is a very slow approach, yeah, because whenever you create new molecules, you have to create the conformations, you have to dock or calculate scores with these, and then create the next generation. And of course, you never know how well you really do because this is heuristic. You don't know how close you are getting to the optimal results. And since these spaces are extremely large, you have to run these things quite some time. But as a basic technology, it's always good to have something like this. Okay, so going more the algorithmic way, the story actually starts with feature trees, and this is now 20 years old. And this is actually not my slide anymore. So this is from Franca. We developed this, so Martin Stahl and myself, during my postdoc time. And actually, the approach at that time was built for completely other spaces. It was made for spaces which were created by shredding molecules into pieces. And then the method more or less existed for several years, and now it's basically used for this make-on-demand compounds, which is obviously much more interesting than recombining fragments where you actually don't know whether you can synthesize them well or not. So the algorithm behind feature tree fragment spaces is quite complex one. It uses two levels of dynamic programming, and or was introduced already, as I said, in the 2000s. I will not do this now, of course, but the idea behind it became important just very recently, as you will see in a moment. Okay, so the search machinery is based on feature trees, which is a pharmacophore-like descriptor. It has several advantages. You have a more like a fuzzy descriptor, which describes the relative arrangement of functional groups, which is, of course, very interesting to search in this way. But obviously, there are scenarios where you want different ways of searching molecules. And for quite some time, there were basically no other machinery available to go through this space in a deterministic way, so that you really get the highest ranking molecules out of it, except of this feature tree approach. But then, since we noticed the popularity and the impact of this make-on-demand catalogs, we started a few years ago to develop new algorithms for this approach. And 2020, so last year and this year, we really had two big breakthroughs on the algorithmic side in analyzing chemical space. So this is actually my view on the problem. So if we are in the early phase of molecular design, you basically have the search space where you either look at just a few thousand molecules, you have screening libraries in the millions, and you have the chemical space, which can go up very, very high. Yeah, and then you have the kind of search queries. Yeah, sometimes you look for topological similarities or fingerprints. You look for certain core structures. We have reduced graphs we just saw with a feature tree approach. Then it slowly goes to 3D. So you basically use the shape of molecules or pharmacophore or docking calculations. And these are the 6 major routes for picking molecules from libraries. And for all, we have quite reasonable good software if it goes up to screening capacity, so up to the millions of compounds. But if you are beyond that, then it gets more tricky. Yeah, so we had the feature tree approach already for years, but that was the only one we had until very recently. Yeah, so now I will basically show you how to actually search with topological similarity, which we just published just a few months ago. And in the second part of the talk, I will show you how you can actually search for maximum common substructures, and which also includes subgraph matching. I will not talk very much about the structure-based part here. Okay, so the approach we use for topological similarity searching is called SpaceLight. And so here you see the paper if you want to read the more methodology details behind it. And the idea behind SpaceLight is as follows. We make a fingerprint-based search, and I'm pretty sure most of you know ECFPs, so the Morgan fingerprints or circular fingerprints, which are frequently used to search for molecular similarity. Yeah, we have a different variant of that, which is called a CSFP, which is a connected subgraph fingerprint, and the difference between these two is that ECFPs are purely radical, so they are always go spherical around one atom, and the CSFP creates all kinds of substructures, which has some advantages here, which are on the methodology level. And of course, the set of features is much richer with such a fingerprint. Okay, so the idea is as follows, and it was actually already the idea 20 years ago. We have to really work with the combinatorial nature of these fragment spaces. So the large numbers basically come from the exchange of reactants. We have seen it already in the last talks. Yeah, you basically exchange reactants, and then you come to a very large numbers of intermediates. And if you even have a third reaction partner and the second reaction, you come up with already billions of compounds. Yeah, and then it's already clear why you can easily come up with this huge numbers of different compounds. And only if we really take this into account and develop algorithms which avoid the enumeration of all these molecules, we are really able to keep track with the growing numbers of compounds in these libraries. So for the search by fingerprints, we use a different technology than with the old feature tree approach. We work with so-called topology graphs, which are shown here. So for each of the individual reactions, we create these graphs which actually show which kind of molecular structures exist after the reaction took place. And then for the individual reactants, we have then the pool of reactants you can actually use here in this reaction. Yeah, and we do a lot of pre-processing so that these reactants already look close to what they will look like in the chemical structure at the end. So, and based on this, we can then do the search. What we actually do is we have the query here on the right side. Then instead of creating all molecules from the topological fragment space, which would be way too much, we basically partition the query and then compare the individual partitions to the fragments in the fragment space. And then we have a more complex recombination phase where the fragments are recombined in a way that they create molecules which are highly similar to the query. Yeah, and we basically do this for all possibilities to partition the query, and then you basically get the results. Now, so that's the method in a nutshell. And if you want to know more, I refer to the paper where it is described in more details. So the big question which arises here is, of course, do the results look similar when we do this compared to a true ECFP calculation? And here is the answer to this. So we basically have three example spaces, which are subspaces of the enamine real space. And we basically have hundreds of test queries, and we calculate the similarity with ECFP fingerprints with different radii, also with our CSFP fingerprints, and it's basically always the same picture here. We basically have candle tau values in the hit lists, which are above, so around 0.7 here, yeah, so which is very high. Yeah, so the overlap in the top ranking compounds is in the range of 70 to 80% for these spaces. So given that the ECFP is just a similarity measure, which doesn't have an exact relationship between the molecules, so it's not that there's one similarity measure which is right and the other is wrong. So it is reasonably close to what you really get when you would sequentially go through all the molecules. Yeah, and here's just to explain where differences come from, and also to show you that these differences are not always negative in the sense that you say, well, it's not the same than the sequential search. It is also has its advantages, because a fingerprint like ECFP basically counts features and does not actually notice the relative arrangement of features. So while when you do this in a fragmented molecule, you actually see which features are in which fragment, which actually helps you to get, in my opinion, even better notion of similarity. Yeah, so here's an example. So this is one of our query compounds, which was taken from zinc. You see two molecules which came out of the search, and you immediately see it has a high degree of similarity here. And here is what came out with the Spacelight search. Yeah, so you basically see how this molecule is created in real space from fragments, and how they are basically form the molecules, which are then highly similar to this query compound. You see that there are slightly different ranks, and just to say that these numbers are, the differences are quite low, because we are collecting thousands and up to 100,000 of molecules from these spaces to do processing with these compounds later on. But just to explain the differences, you probably noticed already the differences between the compounds. There's a sulfur atom here, which makes this compound more similar. And here's you have the nitrogen, and then you have this ethene chain here, and this is just located at a different place. Here it's located in the lower part of the molecule, and in the other molecule it's in the upper part here. And this is actually something which is recognized by spacelight. This molecule, the lower one, gets a higher rank in spacelight, basically because if you look at the fragmentation level, you actually see that this group is at the right position. So this plays a role, and the other aspect which plays a role is obviously that you cannot really look over this cut. So here you basically see that if you are standing on this atom here and look downwards, you see the sulfur atom here and the nitrogen atom here, which again makes now this molecule look more similar than that one. And here it basically shows that if you have the fragmented situation, you basically don't see what is on the other side. This is just the one thing one has to accept if you want to do the whole thing combinatorially. But as I said, the effect is very low, and the reason why this is very low is because the environment of these reaction sites is usually very similar in the molecules. Okay, so just to show you that search is exact. So if the molecule really appears in the space, you will find it. So whenever you have a score 1.0 molecule, you can look it up. In theory, it is possible that you have something very, very similar but not identical, but we haven't found a single case where this happened. So this is basically here. So usually with a 1.0 score, you have the identical molecule, and if you have 2 or 3, you could actually look up which is the right one. As with fingerprints, always is the case. So you can always have molecules with the same fingerprints which have slight structural changes. And then here's just another example to basically show you the variety of molecules you get, and you see the typical behavior of fingerprint-like similarity, where you basically have chains of different lengths here, but very similar substructures. The good thing about it is that when you search for these molecules and you find them, you get also the information what the building blocks are and which reaction could be used. So here's, for example, a search you can do then when you, for example, have spaces like knowledge space or so, where you can basically then get this information also out of the search process. Okay, so computing times. So Spacelight is quite fast, so we have run times in the order of seconds. The blue bar is something you would more or less ignore. This is only need once to initialize the whole system, but once it is running, you can ask your queries. And here are just 2 different spaces. So it's a real space here with it's an older version with 13 billion products. This is the one, this is the knowledge space, space with 10 to the 15 products. And you see that you can search these spaces usually in a few seconds. And you basically only need a regular computer for this. You don't need a big machine actually to do these searches. Okay, so just as a final remark, you can do interesting things here. This is actually the first time where we looked up, for example, all molecules from drug bank and see which molecules appear in real space. You can do this calculation just in a few minutes and basically get an assignment for all molecules in drug bank with a relationship to enemy real, which one you can buy, where you have similar molecules, and where you have only low similarity. And although these numbers are very high, I just want to mention here that, of course, you see here there are still lots of molecules where you have only low similarity to these molecules. So 10 to the 10 to the 10, 10 to the 11, which sounds already extremely huge, is still a small space compared to what we can create in theory. Okay, so I promised that I also show you something completely new. So this is actually the first time I will talk about a new approach which goes into the direction of maximum common substructure search. And this is the name of the tool, which is called Spacemax. This is completely unpublished so far. And this is actually what we do. We have the chemical space here. You basically start with a compound, and we are searching for so-called connected maximum common substructures. Yeah, so here from these structures, we basically have the one restriction that we have a s-cyclic bond matching. So whenever you have an s-cyclic bond, this matches to an s-cyclic bond, and vice versa, so cyclic bonds only to cyclic bonds. And then we basically dig out all the molecules from the spaces which have a high maximum common substructure. So to explain the similarity measures we are using, so we are counting atoms here. So we have here the molecule with 14 atoms as a query. We have then, if this molecule, this pure alkyne chain would be in the database, which is not, but in case it would be, you would have a matching size of 7 atoms, which would be here this chain part, and then a target size, or the size of the molecule in the chemical space of 11 atoms. And so either we are just looking for the largest common substructure, which is then a measure with M size, or with the number of atoms. And then among these, we are usually sorting by ascending target size, so small molecules to large molecules. Or we use a similarity measure, which takes the molecule size divided by the size of the two molecules minus the matching size we have found out before. And this is a little bit like a Tanimoto coefficient and helps you to really find more interesting examples. I will show you an example shortly, which shows you the advantages of the MCS similarity measure. Okay, so how is Spacemax working? As I promised at the very beginning, it has some similarities to the feature tree approach. So first of all, we have our internal library for connected MCS calculations, which is called Rarey. And then it uses this as a subcomponent and combines it with one of the dynamic programming schemes from feature tree fragment spaces. We do precise calculations when you are looking at the matching size of the maximum common substructure. It gets heuristic when you are looking at lower ranks of MCS similarity, because you never know what the influence of the whole molecule in the space. And then a good thing is that we already entered or put smarts-like features into the compatibility check. So Spacemax is actually more than just a substructure search engine or a maximum common substructure search engine. You have all the variability of smarts expressions of many of the features, like and or relationship between atom types and these things. Yeah. And the strategy, basically, we are cutting bonds as before. We have a specific sorting function here on the bonds, and then in this order we are processing them. We basically match fragments from the space to the cut molecules here. And whenever we find another cut, we actually look up the information we have calculated before. This is the dynamic programming step here. And based on this, we actually create our result list now by pairing fragment lists along all these cut bonds. And then we actually have to do a second round of similarity or MCS calculations where we have to check whether the query exists in one of the individual fragments, where we basically have to check all the fragments individually. So that's just, again, in a nutshell, how the method works. Okay, so let's look at a few molecules. Here is a query compound. We have used compounds from this publication. So Uta will talk here after me. So you know already a few of the molecules. They are actually used for the comparison of spaces. So this is the query. We worked with the galaxy space as well as with the enamine real space. So this first example with the galaxy space. And here is just the first hits you find by MCS size. So the number of atoms count, yes, the maximum number of atoms in common between the structures, and these are the molecules you find. And the disadvantage of the MCS measure is that it does not take into account all the other parts of the molecule. So these hit molecules get then, of course, very large. Yeah, and this is actually the reason why we use this MCS similarity a lot. Here it's again the same search. Now we look for MCS similarity. It's not only the number of atoms we match, which is important. It is also the size difference between the molecules. Yeah, and now these are the molecules you get, and you actually see that they are, of course, more similar than the one you have seen when you just look for the MCS size. Okay, so you can do a lot of interesting things with this kind of search now. Before I show you another example, here are computing times we actually see. We are in the middle of optimizing the code, so we are pretty sure that we will get the computing times even a little bit lower. We are able to parallelize the code to a certain extent, not perfectly, but to a very good extent, and you basically have runtimes which depend a little bit on the number of molecules you want to get out of it, and which are then in the order of typically minutes. Yeah, it goes faster if you look for MCS size only, and it gets even faster if you do a real substructure search, and then you basically are in the order of seconds if you have a reasonable machine available. And all these calculations were done on 15 billion compounds with a real space on reasonable machines with this number of cores here. So here's an example, and this is actually was done by Raphael from Biosolve IT. So we gave him the tool and asked him to try what he can do with it, and he actually has done a study and actually shared the slides with me. So the idea here is he took this publication here where the authors looked for similar alternative compounds, make a classical SAR analysis around a hit compound, and we thought in a virtual experiment how this could be done also by accessing chemical space with Spacemax. So this is from the publication. So this was the original hit compound here, and these were the two R groups of the molecules, which are combined by this amide formation. These are the alternative R groups on the left and on the right-hand side, which ended up in 90 different analogs by combining every R group from one and the other side. Okay, so what can we do with Spacemax now? So we basically start with this hit molecule. Here it is shown again. We basically create smiles query out of it. So we don't use the smarts features right now. We basically just write up this molecule here, and then we basically ask, what do we find in chemical space? Yeah, and so we do just looking for the largest common substructures in the chemical spaces. So the first one was on real space. Here, 17.6 billion compounds. It took about 2 minutes to process this to actually create 50,000 molecules from this space with the largest possible MCS similarity to these compounds. And with the galaxy space, which is a little bit smaller, we are able to do this calculation even faster, yeah, and have another 50,000 molecules. And then you can actually look at these molecules. We have 100,000 now. You could use classical filters, for example, filter like for certain lead-like properties, similarity to the original compounds, and also the similarity to the lead compound. Here you see in the slide the order of these molecules given just by the MCS similarity, and you actually see that you have here this 1.0, which actually shows that the molecule is part of the space. Yeah, if you see these bars here, they basically shows you that there are lots of molecules with the same MCS. So here, for example, yeah, so we have more than about 2,500–3,000 compounds, which is exactly the same MCS size and the same molecular size, which gives you another hint of how big the space actually is, how much you can actually collect from it. So by removing all scaffolds we have seen already in the original compounds, we still end up with about 890 new Burmese-Merkel scaffolds, atom-type Burmese-Merkel scaffolds to look up and continue to work with. Yeah, so we found also most of the
Matthias, you have 10 minutes left.
Okay, most of the molecules we have here seen in the study. So we found more or less all of the R groups, and 40 of the 90 compounds were actually available in one of these spaces. And we also found a lot of new molecules here. Just to show you that sometimes also the other search methods are of interest. Here we have the feature tree search, which find 4 additional molecules. And here's the Venn diagram, which basically shows the overlap between the searches. So, of course, the top-ranked molecules are highly similar, but also you find lots of other molecules if you search by MCS, by fingerprint similarity, or by feature trees. Yeah, here are just 2 examples which explain also differences in the search process. Classical fingerprint hit, here you have an extended chain which cannot match by a substructure search. Feature tree, where you have differences here in the relative arrangement of functional groups, which cannot be found here by Spacemax as well. So it makes a lot of sense to just basically depending on what you want to see, to look up, to use one or the other method. Okay, so that was the MCS story. I think this is a great tool. Now I have slides for the 3D part, but basically I will now switch over this here. I think see whether I can basically, no. Okay, so okay, so this is our structure pipeline, structure processing pipeline. And obviously the next thing is to combine chemical space search with 3D searching. Yeah. We do already some kind of fragment growing approaches, and this is also something I will skip basically now. First paper was published here already. And just to wrap up, this is the picture how it looks like today. Yeah, it didn't look like that a year ago. So we really have made progress in searching chemical fragment spaces now. So the pure cheminformatics approaches are solved. So we basically have all these methods available, and you don't need big computers for it, which is, in my opinion, always very important. And this is actually the way to go. Yeah, we will certainly spend now time and try to find good methods actually to do 3D kind of searching in chemical space. Okay, so with this, I would like to end and thank the people who are participating here. This is how group pictures look like today. You can imagine why. So this is Robert here, which have done Spacemax, and I talked a lot about Space Light, which is done by Louis, which is standing here in the lower row. And my thanks especially also goes to Raphael. We talked with him a lot about application scenarios for the different tools. And with this, I'm done. So thanks a lot for your attention, and I hope it was not too much over time because I couldn't use my clock here for some reason.
Thank you so much.